Assalamu alaikum warahmatullah. So we'll be starting this new topic today, that is quadratic optimum regulator problem. It's related to the quadratic optimum regulator system. So this method, quadratic optimum control method, is a systematic way of computing the feedback control gain matrix K. So basically, so far whatever we have seen using the pole placement method, pole placement method, okay, to design gain K. So now today we'll introduce another method that is called quadratic optimum control method. Quadratic optimal control method. Okay, so what is the uniqueness of this one is basically this one gives us a systematic uh, way of computing the gain. So systematic way of computing A. So in this case, let's define the problem first, and then we'll try to solve it. So problem, linear quadratic optimum regulator problem, or quadratic optimum regulator problem. So if a system is given like x dot equal to ax plus bu, as we already know the system, but then our objective is to determine k such that it will give you optimum input signal ut equal to minus kxt. Basically, state feedback system with the gain state feedback gain k. And this time, the problem, regulator problem or quadratic optimum regulator problem, is related to minimizing or subjected to minimizing performance index J. So in this book, they are calling it performance index, but in more general term for this is actually cost function. So we'll keep for now as a performance index, which is J times, which is J equal to 0 to infinity, your X star, or which is also sometimes may be referred as a transpose. So X star Q star X plus U star R U. So this star may be considered as a conjugate transpose, or in case of linear real valued matrices can be considered as transpose. So basically, now there is two terms introduced. The first one is Q, is a Hermitian matrix, or real symmetric matrix. Okay, so Q can be also both positive or semi-definite. So we can write that Q maybe something like this. Okay, so next is R is mm, R is same definition, is also Hermitian or real symmetric matrix. But in this case, it is only positive definite, not uh, semi-definite. So basically, you can just write R is greater than 0. So well, maybe you don't have any idea what is definiteness of a matrix, but just for now, you realize that metrics cannot be just said positive or negative. So there has to be said differently because they're not just a single entity. So that is why they are called as a definiteness. So whether it is positive definite or positive semi-definite or negative definite or negative semi-definite. So in this case, the Q and R, they are positive definite metrics, or Q can also have positive semi-definite. Okay, so now, and also this term here, this one stands for the energy input. So consumption of your actually energy, that is being expenditure of your energy of the control signal. So you can call this one as a expenditure, or it accounts for expenditure of energy of the control signal, of energy of the control signals. Basically, they refer it as a control input signal. So because U is there, so it refers to the how much energy you're putting into the system through the input. So that accounts for that. And the other term here, this actually refers to the error. Okay, so how much our X is deviating from the ideal values. So now the Q and R, they're actually relative relative weights, weights of error and energy expenditure. Okay, so whether we'll prioritize the error or prioritize the expenditure of energy, that depends on the what value you're choosing for Q and R. So both of them has to be positive definite commonly, or Q can also have a value that is positive semi-definite. That means it can also take the value of 0. So now let's figure out our problem in hand. So our problem is figuring out U is which is basically ut is minus k xt. This is what you have to figure out. Optimal control input. Optimal control input, you can say, or simply control signal. And x is already known. So our ultimate target is to determine the feedback gain. So this is already we have done in full placement, but we have an account for the cost function or optimized value of k. We just assumed with our desired location, we figure out the location. So now we are also maybe given some constraints or maybe given some optimization to do, maybe reducing the input energy or reducing the error. So based on those values, we have to pick a specific value of the gain k that will give us the minimized value of the cost function or performance index function. Now, our ultimate objective is to find out the k in a systematic way. So now let's solve this problem. I think problem is well understood what we meant. Our problem is we have a system x dot equal to x plus bu. We have to find out the k so that we can determine the input signal or control input, and that is subjected to minimizing the cost function or the performance index. So this is our problem. A lot of things may be new, something you haven't read before, but don't worry, we'll gradually explain each of them with the mathematical problems, so that will be easier in that case to understand. So now let's start solving the problem now. So first of all, let's plug in the value of the input ut into our system equation. So that means x dot equal to ax plus bu. So this is our system. So we know that our bu, u is basically the optimized value. So that gives us x plus x minus basically bkx. Order is important because all of them are either matrix or vectors, so don't just change the order. So now, in this case, we already, this equation is already known to us. We have used several times before. So if we are assuming that this matrix, which is our new system matrix, is a stable matrix. With that assumption, we proceed further because later we have to. Also, it's true if the system is not stable, then there is no point of optimizing anything. So that is why first assumption is always the case is that your system is stable. So now we also have to substitute this value of u to our performance index. So that means ut is minus kxt. We'll be plugging that into our performance index function j, that is 0 to summation of 0 to integration of 0 to infinity x star qx plus u star r u dt. Now u values has to be replaced. So let's replace these values. X star qx plus minus basically kx star r minus kx dt. Okay, so one thing just to remind you that if you have this okay, you can also give some other, just keep it simple. So if we have a case like this, transpose of the product of it, then if you separate them, the order will be reversed. Okay, so x star, then k star. Okay, similarly, if it is a star, b star, and then that if you try to combine them, b will be coming first, so order will be reversed. Just a quick note. So now because we have to break this one, so that is why we have to apply that one. So 0 to infinity x star qx minus and minus will be multiplied with it, so it will be becoming plus. So x star k star r kx dt. So now x star and x is common. X star is pre multiplied and x is post multiplied. So you can take common. So you have, in both cases, we have pre multiplied with x star and post multiplied with x. So x star taken common, then q plus k star r k then u x dt. So now we're going to find out the value of the performance index j. So since it is integration, if somehow if this parameter here can be represented by some form of derivative, then we can easily say some form of the derivative which we can represent like d by dt of something, and integration and the derivation will be canceling each other. We can easily find out the solution of it. So that is why we are just assuming that, or let's take x star q plus k star rk x equal to minus d by dt of by dt of x star ex. Okay, so now uh, what is p? Let's assume that p is also a semi-definite matrix, or and also p is a Hermitian matrix. Okay, so I haven't defined Hermitian matrix. Basically, Hermitian matrix is a matrix whose conjugate transpose is basically, which is P star, is same as P. So if you take the conjugate of P, this is defined by conjugate of P, and then take the transpose of it, that will give you P star, and P star will be equal to P. Okay. So in case of real matrix, conjugate doesn't come, all the parameters are real. So this is true for Hermitian. A special case of Hermitian is P transpose equal to P. If all the parameters of P is real, then we can simply write P transpose equal to P. So this is in case of real matrix. All the entities of P is actually real number, real matrix. And in case of complex matrix, we can have P star equal to P. Okay, so now let's X is in general a real value function, so that is why real values vector, so that is why in general X star represents simply X transpose, nothing else. So what we have here is now just simplify this. This was not okay. So X dot star ex minus you have x star e x dot. Okay. So now we have x dot. So we know that our x dot equal to, we already figured out x dot equal to a minus bkx. So now replace this here. So this will give us minus x a minus bk x, whole thing will have transpose or conjugate transpose minus p x minus x star p, then simply a minus bkx. So as we said, that we already said, if we have two multiplication, the order will be reversed. So it will be minus x transpose a minus bk transpose P x minus x transpose P A minus BK x. So again, you can see that there is both the term is P multiplied with x star and post multiplied with x. So you can take common again. So you can write that minus x star A minus k star P plus P A minus bk x. So now if you compare these two equations, you can see that you can find out what is the middle term is here. Okay, so you can see that this is equivalent to this. Also in a negative sign, don't forget about this. So now let's write it. What we have obtained out of it is A minus bk transpose or star P plus P A minus bk is equal to minus Q plus RK star RK. Okay, so we call this equation, because we have prepared this equation for some time, so we call this equation as equation A. So now, if the matrix A minus BK is A minus BK is stable, then we can easily show that there exists a P matrix, a positive definite, positive indefinite matrix. Okay, that satisfies equation A. Okay, so system has to be stable. Okay, so in the reverse way, what you can say that somehow if we have a positive definite, we can find a matrix P and that is positive definite, then also we can say that A minus BK is stable, but system is stable. So vice versa. So what is our procedure now? Our procedure is to figure out P. So ultimately what we have to do now, we have to determine P and check for its definiteness. Okay, so we are looking for a positive definite P matrix. So somehow it may happen that more than one P you can obtain. So more than one P can satisfy equation A. But we are looking for only the positive definite one. So only positive definite one. Definite one we take and discard rest. Okay, so now our ultimate objective is to basically figuring out that P matrix, and also in the same way figuring out what is our performance index. So now since we already figure out our J, so our J is basically can be written as 0 to infinity x star q plus k star rk dt. So this is already what we have. Then we have figured out that this entire thing can be replaced by minus d by dt of your x star px dt. So the derivative and the integral will cancel each other. So we can just simply find the value of x star px with the limits. So that gives us minus x star infinity, x star infinity, px infinity, more minus minus will be plus x star 0, px 0. So since our system is stable, A minus bk is stable, that means our state eventually will vanish. That means x star will be going to 0. This all the states will be going to 0 since the system is stable. Since A minus bk is stable. Okay, so we can discard this component. So ultimately, our J can be written as x x star 0, p x 0. Okay, so very easily you can find out our performance index only in terms of initial condition, initial state x 0 and p. So ultimately, as you have seen, the P matrix is the thing that we have to determine. This is our way forward, basically. Okay, now to proceed with our quadratic optimal control problem, we can assume that our R can be written as T star T, where what is T? T is a non-singular matrix. Okay, so non-singular matrix means somehow we have to take somewhere in the way forward T inverse. So non-singular matrix is if you take the inverse of it, it will not be 0. So that is why it is called as non-singular matrix. Somehow you have to take the inverse, and the determinant of your T should be 0. Just a minute. Okay, so now basically determinant of this cannot be 0. So because we know that if you take the inverse of any matrix, so you'll have adjacent of that matrix where the determinant, so determinant cannot be 0. So what bottom line is, somehow we need inverse matrix. So we have to make sure that T cannot be a singular matrix. So it has to be a non-singular matrix. So now based on this idea, we can replace the value of the R into the equation and then proceed with the solution. So from the equation A, we can write from equation A. That is A minus BK trans star P plus PA minus PK was equal to basically minus Q. So we can take it in the other side. So it will be So plus Q plus it was K star R K. Now we just replace the value of R with T transpose or T star T. So basically, and also we have to apply the star here. So will be, this one will be reversed. So A star will be as it is minus K star B star after reversing the order. Then you have P multiplied plus P times A minus PK plus Q plus K star T star uh, KT equal to 0. So you can write this one as just multiply. So A star P minus K star B star P plus PA minus PBK plus Q plus K star T star KT. So basically we have to somehow optimize or minimize this equation. So that is why we try to figure out the parameters that can be optimized. So now A star P plus PA, then you have plus K star T star AT minus K star B star P minus BBK plus Q equal to 0. So this one we want to divide this three as a product of two component, which is the transpose of one multiplied by the same component. So what will be the parameters? You can write in one line like book, but it will be difficult for you to understand. But as you can see here, somehow this is the first term will be combination of these two. So basically you can say that this can be your okay. So somehow I think I made a mistake. So no, this order is important as I said. Somehow the order is been not maintained here. So that is why if you make any mistakes, you'll see that final outcome is not coming as expected. That is why order is important. Okay. Now, so it will be basically T. It will be TK. So TK. So ultimately TK. So now one of the parameter has to be TK in both cases. And as you can see that TK transpose will give you K transpose and T transpose. So one of them has to be TK. So the other parameter has to be some common factor should be there. And that common factor with the subtract because of this minus signs. So now say that this is your question mark parameter. So that we know that this parameter multiplied by this question mark parameter in the other one will give this parameter. How we know that? Because this one has K star. So you can say that tk star multiplied by this question mark component, that should give you either of this, either this one or this one. But as you can see that it will give you k star, t star, then multiplied by question mark should be which parameter then? Because this one has k star. So we can see that instead of this one, we have to take this one. So this will be your k star b, b star b star. So k star b star b. So you can take inverse of k star in the both sides. So if you take inverse of k star in the both sides, so k star inverse, k star inverse, inverse, then this parameter can be cancelled. So basically t star with the question mark parameter that we are looking for is equal to b star b. So if you take it in the other side as inverse, so the parameter that we're looking for is basically t star inverse b star b. So as I said, somewhere in the down the line, we have to figure out the t star inverse or t inverse. So this is why we have said that T cannot be a singular matrix. So basically, we already figure out what should be this parameter here. So we can write this equation as A star P plus PA plus as a product of TK minus T star inverse B star P multiplied with oh, don't forget the star. Then Tk minus the same parameter T star inverse B star. So now if you do this, you're going to see that one additional component will be added after multiplying basically this one and this one, additional component will be added. So that one we also have to subtract. And somehow that additional one will be P B R inverse P star P. Okay, and then finally you will have your Q equal to 0. So maybe you are confused. One thing we already figured out how this one will be coming, but what about this one? And what about this one? For that, you can just simply multiply these two components. And if you multiply these two, then you're going to see that these parameters are coming. But if you want, I can also try to illustrate that like so what you have is order is again important, their matrix. So TK, TK, just for you is, it will be TK star, the first one we're writing, TK star minus the whole thing, T star inverse B star P, whole thing will also have inverse because the order will be changed again, so you have to be careful. Then this has to be multiplied with your TK minus T inverse, T star inverse V star P. So this one and this one is already multiplied and we obtained this parameter. Okay. And then we multiplied this parameter and we obtained this. So what is left to show is multiplication of this one with this one. This should give us this parameter, and multiplication of this one and this one should give us this parameter. Okay, so let's show this. Again, this is just note. As long as you can memorize, that's good. But sometimes you may not memorize, and in that case, you'll be in trouble. So that is why I'm just illustrating every bit of it. So now you have to reverse it first. So E star, then B star, star, then you have T star inverse, then you'll have another star. Okay, so now I'm just simplifying this first. So now it will be P star, B star and star. If you have double conjugate or double transpose of a matrix, it will give you original matrix. So that will be basically B. So now this will be B. What about this? Another note is that if you have transpose and inverse, so order is not that important. So ultimately you can do one, then do the other. So this is same as taking the inverse and taking transpose. Okay, so applying this, what you can do here is the outer two can be reversed. So basically T transpose is there, then another transpose goes, then we go with inverse. So ultimately it will be P star B, then T transpose T is T, so simply this will be T inverse. So this is our first term here. And now what you have to do is you have to multiply this with this. So if you simply multiply this with this, then what is we are coming is P star B T inverse TK. So T and T inverse, they'll be combining with the identity matrix, which can be just a one in terms of matrix. So we can write P star B K. So you may be saying that this is not same as PBK, which is the case here, but one definition just to remind you that for a symmetrical matrix, P star is same as P. So we can say that this is same as your PBK. So that is proved, no problem with it. Now, second thing is we have to obtain this value, this one. So now to obtain this one, what you have to do is you have to multiply this one with this one. So ultimately, this one with this one, multiplication should be enough. So now what you can do is we can multiply these two to obtain. So E B E inverse. You can write star or P, same thing. So you can write the same, it doesn't make much difference. Then you have T transpose P star inverse B star P. So this is true for P because P is a symmetrical matrix, but this is not true for B because B is not a symmetrical matrix. In most cases, it is a vector. Okay, so or one-dimensional matrix basically, either one row or one column is there. So now what you can do here is you can take common of the inverse in the reverse order. So basically, if you have inverse T and T star inverse, then it will be T star inverse reverse order. Order will be simply changed, T inverse, something like this. So what you can do here, you can take common in the reverse order. So it will be PB T transpose reverse order inverse B star. Simply you can write P B and T transpose T is nothing but R. So R inverse B star P. Okay, so this is same as what is given here. So this is the additional components. We also subtracted that. So now basically this equation, which we call equation B maybe, so that one has to be minimized with respect to K. So what we're trying to do is we're trying to minimize our performance index with respect to K. Minimizing the performance index is nothing but minimizing same as your equation B. So equation B can be minimized only by minimizing this middle term because rest of them are more or less positive, so they cannot be minimized. So ultimately this one we have to minimize. Okay, so minimizing this okay, so minimizing this or means we have to set it to 0, then find out the derivative, then that will give you the minimum value as we know from our previous knowledge, but minimizing, minimizing J with respect to K means ultimately minimizing Tk minus T star inverse B star P star times Tk minus T star inverse B star B. Okay, so minimizing this, and as you know, this is simply a product of two component in a metric wise, and that cannot be made. That is always either greater or equal to 0. So as minimizing this means actually taking it equal to 0. So if you take it to 0, then what we obtain is basically Tk minus T inverse T star inverse B star P has to be equal to 0. So this gives us Tk equal to P star inverse B star P. And if you take T inverse in the both sides, so K becomes T inverse T star inverse B star P. So our K, which we are trying to determine, is basically we will reverse again inside the inverse B star. So ultimately, we can write this as a R inverse B star P equal to K. So this is our optimum value of gain matrix K. And using this gain matrix K, we can find out our control input, optimized control input, ut equal to minus K xt. Okay, now what about the equation B? So in the equation B, for the optimization, this multiplication term has to be 0. So we can make this term, vanish because of the optimization or minimization. So ultimately, rest of the parameter will be as it is. So rest of the parameter will be, so one note is this what we have achieved, how to determine the K. Based on the determination of the K, we achieved our desired control input. As now, what is our rest of the equation B? So equation B becomes equation B becomes A star P plus PA minus PB R inverse B star P plus Q equal to 0. So why equation B will be required? Equation B, there is a name for this one as well. This is also known as a reduced Riccati equation. Reduced matrix Riccati equation. Okay, so this equation will be used for determining the matrix P. As we know that the matrix P has to be positive definite. So if P matrix is positive definite, then the system or A minus BK matrix, system matrix, will be stable. System or system matrix will be stable. Okay, so our problem solving strategy will be simply use strategy will be step one is I use reduce matrix Riccati equation to find E, check for its definiteness. Yes, so this is your step one, and if there is definitely positive definite, we can say that our system is stable. And finally, using the P value of P into equation, using the equation K equal to minus R inverse B transpose P to find the K matrix, to find control input as well. Okay, so this is how we have to approach to our problem. So this is based on the minimization of the cost function, but cost function cannot always be like this. That can also have different variations. So another variation of the cost or performance index or performance index, if somehow you are trying to introduce the output vector instead of the state vector, you can also do that. That means we can write our performance index j equal to 0 to integral 0 to infinity in terms of output y transpose or y star qy plus u star ru dt. Okay. So in that case, you simply have to replace y equal to cx, ultimately j will be 0 to infinity. Then you are going to have cx star, just reverse the order, then q cx plus u star ru dt. Okay, rest of the problem is as before, so we don't have to discuss much about it. So let's solve the. This is the necessary theory for solving the quadratic linearization problem or potential optimum control problem.